Hello and welcome to MEL Science, most specifically MEL Chemistry. My name is Dan and it's absolutely lovely and a delight and a joy to have you all aboard. I'm just going to shift my screen here so I can see who's on board here. Cool, so just to make it a little bit more personable, I can see Tracy Wessel. Now, you don't look like a Tracy, but I've got a Potters, I've got Kirsten and Ed, I've got connecting to audio Alex. I've got Sarah, I've got a Julie, I've got an Arthur, I've got a Sarah and another Julie, in fact. I've got two Julies on team here today. This is a live webinar. If you would like to make it a little bit more personal, aha, Andrew, Jake, where have you been, Jake? Well, absolute joy, lovely to have you on board. Lovely to see you. So if it is a live webinar, so if you want to make it a bit more personal, you can switch your cameras on. Hello, Julie, and the gang. There's the gang, the Julie gang. Hello. The Potters, and if you don't want to put your webcam on, that's perfectly fine. You can grab me in the chat. I'm just going to move the chat box just down on my screen. I know that you can't really see what I'm doing here, but just to make sure that I can actually see. So Sarah says, hello, good, lovely to see you. Yeah, so again, you can communicate with me in the chat, and that would be absolutely superb. And if I don't catch your chat messages, just keep saying it again, or poke Ash, who's the adjudicator behind the scenes, and he will then prompt me to ask the question or answer your questions again. And Ted and Adam have also joined, which is amazing. Thank you so much. Okay, and just one last little thing is that if you want to speak to me at any one particular point, you can just put your hand up and say, ask to unmute, or ask a question or something like that, and then I can unmute you and you can ask a question. Okay, cool. Right, is everybody okay to start with? Today we are going to do elements. So elements is the box of tricks that we're going to be looking at today. So elements. And for this, there are a couple of extra little things that we need to get through elements. This is the most fundamental, as it were, a box of chemistry that MEL does, of course, because elements are the fundamental bit of all chemistry. They underpin everything in the world and the universe around us. So without much further ado, we need a couple of extra bits and pieces today. I'm just going to change my screen to show you what those might be. Good. So, without much further ado, we do need today, you need some ice. So you need access to some ice or your little frozen water bag. You need about 2 or 3 ice cubes. You don't need very many, but you do need some ice. You also need some access to some cold water. Okay, some cold water. And then in no particular order, the kit from the kit, okay, all of the stuff you need. Of course, the first thing is we need some potassium iodide, so make sure you've got that. You need some sulfur, some powdered sulfur. You need the copper sulfate. You need the calcium chloride. And you need the sodium thiosulfate. You've got a little tiny pack, a little wonder pack of carbon here as well. So we need that from the box. 3 spoons, a candle, the empty candle holder. This is a little reaction vessel, effectively. You need some stirring spoons. You need this little paper clip. Need a little paper clip. When you've got one of these little paper clips, now this paper clip, of course, for those who are experienced MEL users, the paper clip's normally using to put the plug down. Andrew, how important is the ice? Can you do experiment without it? Jake, it's you do kind of need the ice if you've got an ice cube of some kind or scrapings from an ice bucket. However, if you don't have the ice, if the cold water could be really super cold, that would be great. With your paper clip, if you could just bend the paper clip a little in, so it'll fit in properly into the dish, that would be great. So don't leave it completely out, so just bend it a little bit in like that. You do need from your starter kit, though, you need your heating stove and the lid, and you will need access to a lighter. So you'll need access to a lighter or some matches, because we need to light the candle with that. Okay. One last little thing that just makes it a little bit more interesting is some paper. If you've got some paper, just a sheet of white paper, that would be most useful. Okay, cool. Is everybody okay so far? Yes? Yep. A couple of thumbs up tells me that you're all okay. That's great. Excellent. Thank you. I've got a hand up from Ted. Asked to unmute. Ted, go for it.
Yeah, my starter kit and my elements kit actually just hasn't come in the mail yet, so I don't have it.
Ah. This webinar is being recorded, So when your elements kit and your starter kit come in the post, which is a bit. Have you contacted support@mel.com?
No, I have not.
Very important that even as we're doing this, if you put support@mel.com and just say, hey, where's my kit? Where's my elements kit? They're a very, very helpful team. They will make sure that is whisked off to you in the post and find out where it may have disappeared, if that's okay.
Thanks.
You're very welcome, Ted. Thank you. And Sarah, we're just watching. Sarah, yeah, no problem at all. No problem at all. Again, this is being recorded, so you can catch this recording the following day and from here on after. Okay. So without much further ado, and Adam, hello, Adam. You're there as well. So hang on and welcome and thank you for joining Mel. So I'm just going to move all this lot to one side. We're just going to start very gently. I'm just going to move all this equipment to one side. So all you need to start with is this rather wonderful little box here. Now, this is a bit of sort of talky, showy and explain about this particular element. So the whole outcome from today is looking at the whole of the periodic table of elements that are behind me. And in this box set of elements, we are looking at non-metals. Okay, so basically the whole of the periodic table is divided into metals, so all of these things here are metals, and then on this side here you have the non-metals, and between the metals and the non-metals you have things that are called metalloids. Okay, they have some properties of metals and some that are not properties of metals. Okay, in all of the elements that we're looking at today, so today we're looking at 3 non-metals. We're going to look at carbon, we're going to look at sulfur, and we're going to look at iodine. Okay, completely different chemicals, completely different elements, and they all have lots and lots of different properties which you're going to see. Now carbon itself comes in 3 main allotropic forms. So carbon itself has 3 different types. Okay, and if we pop open our little lid here, you will see we've got here what's called charcoal. So it's a type of carbon, pure carbon. And we also have some graphite. Now if we take out this little graphite, you'll see this in a little shape here. If you had that little bit of paper, look, that I showed you, okay, this little bit of paper, you can see that you can draw quite easily with this little piece of graphite. And this is the same stuff, of course, that goes into your pencils. So this is the same stuff that goes into pencils. So there's no lead in pencils, it's basically graphite. And you can feel it's quite smooth and it's quite shiny, okay? If you take out a little piece of the charcoal, you will see that if you draw on this one, look, it's a darker colour, it looks more crumbly, looks more friable, okay? And it's a much more chaotic structure of carbon. And then last but not least, the most orderly of carbon, of course, is real diamonds. So we actually have given you real diamonds. So you can actually pop the lid out on your little tiny lid here. And if you can see, you've got some little tiny real diamonds. So those are actually real diamonds. And actually, just for comparison, I've got a wedding ring here, which you can probably see. I've got some black diamonds in my wedding ring. So these little diamonds are about the same size as my black diamonds in my wedding ring. Okay. Now, if you don't believe these are diamonds, remember that diamond is the hardest substance on Earth. Don't find a piece of glass that you're not too bothered about. But if you push your that diamond on your finger, if you push it hard against some glass, like a glass window, and push it hard down the window, it will actually scratch the window glass. Okay, so diamond will actually cut glass, no problem at all. So that's one little test you can do. Because these diamonds are quite small, it's a good idea to use a hand lens. So if you've got a little hand lens like this, and you don't have to do this now, don't have to do this now, but if you use a hand lens like that, you can see they're really beautiful little crystals. I can't show you that particularly. Maybe if I can just get that. Will that show? No, not quite, not quite. It won't quite show on this one, but if you look with the hand lens, you'll actually see the beautiful little structure of these natural diamonds, and that, of course, is pure elemental carbon. So these diamonds are the same as the graphite and also the charcoal, so the same as the charcoal. And I've got a much bigger one here, of course, to show you. I'm just kidding. That's just a piece of glass. If that was an actual diamond, it would be about £2.5 million, maybe £3 million. And of course, if somebody's offering you a bag of these on the street, just take it to a bit of glass and scratch the glass. And if it doesn't scratch the glass, you ain't got a diamond this size. Okay, cool. So, beautiful element. Now, just before we leave the carbon, on the 10th of November, there's the MEL Science, what's that, carbon? Yes, fantastic. Very nice one, Jake. We've got on the 10th of November, you've got the World Science Day, and they've got the MEL Carbon Lesson. And it's a really cool opportunity to do a whole carbon lesson separately, and it's free, to do this particular lesson. And one of the interesting things that you can do in this lesson is you're going to create so this isn't the carbon lesson, so if you just subscribe to the MEL site and just see the MEL Science Day, I'm just going to move this stuff to one side, look. You're going to create a circuit, look, with just your pencil, okay? So this, because graphite itself will conduct electricity, so graphite itself will conduct electricity, and if I just put that there, that battery on there like so, hopefully, if I can touch that there, you should see the little diode come on. Can everybody see the diode coming on? Okay, so this is just a little demonstration for you, but this lesson's free in the MEL Science, the World Science Day, UNESCO Science Day on the 10th of November. So please do feel free to tap on that link. It's all free, and it shows you one of the properties of carbon, this element carbon. So I'll just put all that to one side. Okay. Is everybody okay so far? Yeah, cool. Right, cracking stuff. So that is, I'd like to spend a bit more time on carbon. I will go through some of the slideshows too. It's the most important element practically in the periodic table, and it looks nice and discreet and serene here. But in fact, without carbon, no life on Earth, no life probably in the universe. This element couldn't be more important if it tried. Okay, so without much further ado, what we're going to do now is going to look at the sulfur set, this element sulfur. So again, for this one, what you'll need is the empty tray, candle tray. You'll need your little burner, your little cooker stand, and you will need elemental sulfur. So this is the element sulfur here. Okay, so that's the one we'll need. You need your candles. Push your candle in there, and we're going to light that in a second. You'll need your paper clip, your empty tray, and one scoop. So one of your big spoons, okay? And basically, hopefully everybody's got that apparatus ready. Yep. Okay. So, and one more thing, we actually also need the little stirrer, okay? So what we're going to look at here is one element, again, one of these beautiful elements. It's a non-metal, of course, comes underneath oxygen, and it's a powdered form, and you can see that it's yellow here. Now, please, you don't need your gloves at this stage, because we're going to light the flame, and then we're going to make a fairly hot stove. So for this one, you don't need your gloves, but you do need your glasses. So please do pop on your safety specs, if you will, at this point. Okay, so pop on your safety specs. So first things first, just give the bottle a little tap, like so, and then just give it a little stir. Now the reason we're going to give it a stir is simply to free up the powder, because sometimes it can be a bit compacted. Sorry, Jake, I can't do this. I'll watch. I'll have asthma and there's a warning. Oh, Jake, really important. And for everybody else, really important. We are going to heat sulfur here. And in heating the sulfur, there will be a little bit of sulfur dioxide come off. And there's also powdered sulfur as well. So that might be a bit of an irritant to your respiratory system. So when you're doing this lesson, it's really important to make sure that your room where you're doing it is very well aerated. So make sure the windows are open or a door is open, okay? So there is a little bit of sulfur dioxide that will come out of this. So please do take care. Jake, yeah, sorry about that, Jake. Okay, right. So just give that a little stir, just to free up the powder, okay, to make it nice and loose. And you might have to do that a couple of times. Don't panic about that. Then what you want to do is put three very healthy scoops into the, so you might have to give that a little tap. So 3 healthy scoops into your little empty tray. So 3 big healthy scoops. So spilt a bit, that's just why we do it on the tray. There we go. In fact, I'm just going to do a little bit more just for good luck. So 3.5 maybe into the tray like that. And then put your lid back on your reagent bottle. Make sure you've identify where your paper clip is. Okay, at this point, then light your candle. I'll just quickly light that. So light the candle with a match or your burner. And please note, look, that this sulfur, this element, pure substance, so there's only one type of atom in this substance here, is a powder, a yellow powder. Most of the rest of the elements, don't forget, are white, silvery, sort of silvery solids. But the non-metals tend to come in lots of quirky little colours. And a sulfur here, in this form, this allotrope here, is a yellow powder. Okay, now what you want to do is get your the mantle top, the mantle lid, and then basically pop the sulfur on the top like that, okay? I should just move this very close, a bit closer to the screen for you so you can actually see what's happening. Okay, now that takes a couple of minutes to cook, So whilst that's cooking, I just want to show you a couple of little slideshows just to introduce the whole concept of elements and why this is such an important lesson for us today. Okay, just switch that light back off. Okay, right. Now, hopefully I can find my slides. Where are my slides? I'll show you. So, the periodic table of elements has disappeared, but the slideshow has begun. So this is the mailbox for elements. Okay, so what does the word actually mean? The word actually comes from the Latin elementum, which means fundamental or rudimentary, okay? And that actually in turn comes from the Greek word stokilion. And that actually means basic forms, the really fundamental simple stuff. Because back in Greek times, they thought that everything was made of earth, fire, water, and wind. Everything had to be made of those things. So even back then, they were kind of thinking, well, what's stuff made of? It must come from the earth, maybe it comes from the wind, maybe it comes from the air, and fire seems to be involved in everything. So there was this kind of rudimentary thinking that the elements, or elementos, everything comes from those sort of four things, okay? So when we look at the periodic table, we're basically, as I say, we're looking at the non-metals, or the metals here. Most of them are metals, about 80% are metals. And then, of course, you've got the non-metals. You've got the gases here, the noble gases, and you've got the halogens. And then, of course, you've got the groups with oxygen and sulfur and so on and so forth, and also carbon, okay? So that's the periodic table. This is the most amazing piece of science, I think, of all time, because basically that is the ingredient for everything you see in space and time. Okay, so basically just a quick delineation. So most of these are metals, and then the rest of them are non-metals. And today we're just playing with the non-metals. Okay, so how did it get there? Oh, actually, we'll just stop there for a second and look at what's happening in our reaction. Okay, and we'll go back to tabletop with Facecam. So hopefully here, look, you can see that the sulfur, look, has started to melt, and you probably get a little sulphurous smell coming off your mix. Now, you just give that a little tiny mix around like that until the sulphur itself is covering the bottom of the little well there, little reaction vessel. If it has, and you can see there's a little orangey colour, there might be a little bit of an orangey colour there, okay? If it has, and it's completely melted and there's no more crystals in it, as soon as you see there's no more crystals anywhere lurking inside it, blow out the candle, and then we're going to count to 3 seconds, or sort of 30 seconds, and then we're going to just drop the paperclip into that liquid, okay? So if it's completely melted, all you got to do is now count for 30 seconds once it's completely melted. So 27, 26, 25, and so on, 24. And then we're going to watch what happens when I pop the little paperclip into the molten liquid sulfur. So this non-metal has gone from a solid yellow colour to a liquidy and slightly tingy orangey yellow colour. Okay? So probably about another 10 seconds, and pop that in there like that. Whoops. almost. And then rather wonderfully, and I'll bring this up to the camera, hopefully you can see that a bit better. You can see that it started to crystallize around my little paperclip. So it started to crystallize around, and you can see those long, thin, sharp crystals. So those long, thin, sharp crystals. So that's what's called monoclinic sulfur. That's what's called monoclinic sulfur. Because sulfur, like carbon, remember the carbon we had graphite, and we had diamond, and we had the charcoal. It has lots of different allotropes, lots of different forms. And this one here, again, sulfur has lots of different forms. So the atoms can form in long chains or in kind of circles or in kind of funny crown-like structures as well. And these are called allotropes. Okay. So that's aluminium, so I can just pick that up and just show you. So it's gone from that funny, really funny structure, that colourless, that sort of crumbly white, yellow solid, to a yellowish liquid with a little bit of orange in it. Now the orange has got 6,8 to 624, sorry, S8 to S24 molecular lengths, okay, groupings, and that's what we see here. And actually this crystalline, you can see those like sharp crystals, that's monoclinic sulfur. Okay, cool. Is that okay? Has that worked for everybody? Has kind of worked for everybody? Hasn't worked? There's a couple of shaky. Oh, yeah, Kristen. Potters is okay. Arthur, Sarah. Cheryl, hopefully Sarah. Yeah. Kirsten and Ed, there's a shaking of heads. What's happened? I'm doing mine. Sarah, are you doing yours? Oh, perfect. Look, Adam, perfect. That's great. Absolutely great. So you can see that's changed form completely. And I've got a really nice picture on a slide to show you how it looks close up. Okay. Right. In which case, we do need the heater again. We need the heater again then to look at a different element altogether. So in this element here, we're going to look at element iodine, so one of the halogens. What is the, Sarah, what is the paperclip made of? Sarah, the paperclip's made of iron. It's made of iron. So that is elemental iron. And of course, when you combine iron with sulfur, you make iron sulfide. Arthur, you're very welcome. You're very welcome. You make iron sulfide. And of course, iron sulfide is very, very famous. I think most of you might have come across. Have you ever heard the term fool's gold? Anybody heard the term fool's gold? Yeah? Fool's gold. So that is iron pyrites, which is iron sulfide. So here, there's a little bit of iron sulfide will form, a little bit, but not very much. And of course, horribly, sulfur compounds can be very smelly. And you know, sometimes when we're coming up to Christmas. Let me, what's one of those funny little green vegetables that we eat at Christmas? Anybody? What's one of the funny little green vegetables that we eat at Christmas? You can ask to unmute, or you can tell me. Sprouts, Sarah says sprouts. I love sprouts. I really love sprouts. But the problem with sprouts, though, is it makes you very antisocial. How does it make you antisocial? How does sprouts make you antisocial? The smell! The smell as well. Well, interestingly, when you eat sprouts, one of the compounds that forms, I'll write this down for you. One of the compounds that forms when you eat sprouts, because they are full of sulfur-containing compounds, but when you're antisocial and you break wind, or dare I say it, have a little fart, this is one of the compounds that's formed. It's hydrogen sulfide. So hydrogen sulfide. So our S has appeared, and hydrogen sulfide stinks because it's very, 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 very poisonous. Hydrogen sulfide is very poisonous, which is why when you produce hydrogen sulfide, when you've eaten some sprouts, is that people don't come towards you with your hydrogen sulfide, they run off. Because it's a pretty unpleasant gas. Okay, so sulfur chemistry in its own right. Fascinating, fascinating area of chemistry. Okay, let's crack on. So the next one we're going to do is going to have a look at iodine. So we're going to do this one here, elemental iodine. Okay, Jake, the sprouts are in the house. I'm not coming round for tea tonight, Jake. I think it might be a bit antisocial around there. Okay, cool. So if you pop that to one side, we're going to do iodine now. So what do we need for this kit? So this is the iodine set. Now, please, before we do this, I know that nearly every one of you has been swimming. And what is one of the chemicals, what's one of the elements they put into swimming pools? What's one of the elements they use to clean swimming pools? Anybody? Asked. Chlorine. You guys are absolutely amazing chemists. Fantastic. Sarah, superb. And Jake and Potters. Yeah, chlorine. So elemental chlorine, of course, is one of the halogens. So the first halogen we have, of course, is fluorine, which is super unpleasant. One of the nastiest chemicals ever. And then beneath that, you've got chlorine, and that's really unpleasant. And then its kind of ugly little brother is iodine. And iodine is a halogen, okay? And the word halogen means salt former, okay, so you form salt. So you know on a Friday when you have your sort of salt on your chips, it's sodium chloride, so it forms salt. Okay, so what do we need for this one? This is where your ice comes in, ladies and gents. So you need your ice here ready, please. You also need some water, and the chemicals that we need for this one are as follows, okay? So first things first, we need the potassium iodide. So this is the compound. Do I have ice? I do not have ice. Sarah, if you don't have ice, you just need really super cold water. It will work with super cold water, okay? Okay, so this is the potassium iodide that we're going to start with. And of course, here is the clue. That's where we're going to get our iodine from, because this is the potassium bound to the iodine, okay? So we need that one. We also need the copper sulfate. So we're going to use a reaction with copper sulfate to extract the iodine. We also need calcium chloride. And most importantly, we need this substance here called sodium thiosulfate. Now, the sodium thiosulfate effectively is to get rid of the iodine, or put the iodine back in its box in a way, and make it nice and safe. So that's really super important, okay. You've got some little thermochromic strips. The little thermochromic strips, of course, are going to go onto your glass beaker. Okay, so if you pop those onto your glass beaker, like so. So we do that first, and then we're going to put our gloves on. Now we're going to put our gloves on and then take our gloves off for this experiment here. So put that onto your beaker. Is everybody okay so far? Am I going too fast? Are we okay? We're okay. We're okay. Cool. We're good. Okay. Just sort of wait, what was that? I have super cold. Sarah, yeah, if you've got super cold water, that's great. That's absolutely great. Okay, so first things first, I'm going to put my gloves on and... Right. So again, you're going to put these on and take these off because we're going to heat the mixture. But before we do that, we need to put our gloves on for the chemicals, the reagents that we're going to be using to create this reaction. So basically, the first part of the reaction is to free up elemental iodine. Now, it's very difficult to see iodine in nature because it's very reactive. But this particular chemical reaction allows us to free up the iodine and then allow the iodine to move from a solid straight to a gas without going through a liquid phase. And that's called sublimation. Or sometimes you can hear it called deposition, but we're going to make it sublime, effectively, go from a solid to a gas without going through a liquid phase. Right, so first things first. If you get a new spoon and you want the copper sulfate first, so I put that here. Just move those reagents to one side. So if you get the copper sulfate first, okay, so push down the lid. And with the copper sulfate, you want two big spoons of the copper sulfate and pop that into your beaker, okay? 2 big spoons, heap spoons of the copper sulfate into your beaker. Okay, like so. So 2 big spoons of copper sulfate into the beaker. Now next, we're going to get the calcium chloride. Okay, now we want 3 big spoons of the calcium chloride. And again, please folks, if I'm going too fast or you've missed something, please don't say, hey Dan, stop, slow down, it'll be fine, okay? That's why a live webinar here it's for you, it's obviously not for me. Okay, so you want 3 big spoons of the calcium chloride. 1, 2, and 3. So 3 of those. Now next, of course, we've got no iodine present in any of those compounds. So now we need to have the iodine. So we need to find the iodine and get that liberated, okay? So now you need the potassium iodide. So now you need the potassium iodide. And what we want for this one, you might find this particular chemical tends to clump together in little sort of crystals. So if in your bottle you've got some little clumps, if you just get one of your little stirring rods here, look, just give that a mash up like so, just to free up any of the clumps, whatever, and put it back into a powder form. That would be great. And then what you want here is one big scoop, one healthy scoop of the potassium iodide, like so. So one big scoop like this. Okay, one big scoop, and plop that in like that. And then put your lid back on, of course. Now, once you've got those 3 powders in there, those 3 reagents, just give that a little swirl around, a nice mix around. So mechanically, just give it a swirl and a mix for about 10 seconds, about 5 to 10 seconds. Alex, I'm glad you think it's excellent. Glad you like this, Alex. This is why you subscribe to MEL Science, of course. So give that a nice little mix around, okay? Now, it might not look as though anything's happening, but stuff is happening, okay? Stuff is happening, so don't panic. But it's cold, it's at room temperature at this point. So what we need to do is heat it up a little bit, okay? So I want you to heat it up a bit. So just give that a good mix around for about 10 to 15 seconds. And I'll just have a quick check to make sure you guys are all okay. Benjamin, you're okay? Julie, family, okay, watching. And yep, you're all good. Super, 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 super. Right, so now next we need to light our candle. So I'm going to bring this whole lot forward a bit. So I'm going to light a candle so everybody can see that more clearly. So please just make sure the candle wick, right, is standing straight up. And then put your heatproof the mantle back onto the cooker. Now, everybody should have noticed, of course, I should have taken my gloves off when I was handling this, when I was burning the flame, but I didn't. So don't panic, don't panic, don't panic. Okay, so now put the beaker directly onto the mantle like that. So put the beaker directly onto the mantle. You have access to some water. So if you get one of your little cups, so get one of the little cups, okay, and put some water into the little cup. So some cold water into the cup, okay. So put about half full, about sort of 3/4 full, about 3/4 full. Okay, put that as a cup, and then pop that into the container. You might already see some faint little wisps of iodine emerging from this reaction. Okay, you might actually see some faint wisps of iodine from that reaction. Now take the sodium thiosulfate, so sodium thiosulfate, and we want 4 big spoonfuls, so 4 big spoonfuls of the sodium thiosulfate into the water. Okay, that's very important. So 4 of the sodium thiosulfate, 1, 2, 3, and 4. Okay, so 1, 2, 3, 4. So that's the sodium thiosulfate, and we're going to give that a little stir to dissolve it. And you should already be seeing some purple smoke. I think you can probably see from mine. I'm just going to turn it around for you so you can actually see there's a little bit of purple vapor emerging already from mine. So give that, those crystals of sodium thiosulfate a stir. So give that a nice little stir to dissolve that. And for those of you paying particular attention, you might see there's some really unusual shaped crystals. So sodium thiosulfate got some really interesting shaped crystals in there. But just as a minor aside, okay? So just give that a little stir till those are nice and dissolved. Might take a couple of seconds. And as I said, this solution is super, super, super important because iodine, of course, is a halogen and they're pretty unpleasant. And that is our way of disposing or putting the iodine back into a kind of safe chemical compound, okay? So that's now pretty well dissolved, okay? So once you've done that, then pop a little bit of ice into your solution, okay, or your little ice bag. If you're using the ice bag, that's perfectly great. If you're using ice cubes, then just pop those in there now, like so. So we're going to cool this solution down. Shall put a bit there, should be right. Cool. Okay. So basically what's happening here is, I said, the iodine itself is being released in that chemical reaction by the action of the heat. The iodine as a gas is appearing, so it's coming out of the potassium iodide, it's being displaced from the potassium iodide. There's also a bit of copper iodide being created in there. But enough of the iodine, the free iodine, is appearing, and that's because you're heating it, it's turning up as a gas. And as the gas hits the cold surface of this container, it will start to sublime. So it goes from a solid, or a gas, straight to a solid. So it sublimes, okay? Now, we need to leave that cooking for a couple of seconds, for maybe about 5 minutes, about 5 to 10 minutes, okay, to allow enough of the iodine vapor to crystallize or sublime as a solid on the wall. So just leave that. But you can have a look at the walls as you see this strange purple vapor appear. Okay, so if you don't mind, is everybody okay so far? Can everybody see a bit of purple? Those who are doing it, can everybody see purple? Yes, 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 yes. Cool, cool, cool. Nice one. So we'll just give, nice one. Lovely, Kirsten. Can't see Potters or Adam or Arthur or Sarah or Alex, but I'm hoping you guys are okay. Andrews is fine and Benjamin's fine. Aha, Adam, excellent, cool, got a thumb, excellent. Arthur's fine, so cool. So just wait, now we're going to wait for about 10 minutes for that to create enough iodine to crystallize on the side of the thing. So if I want to show you a quick slideshow again, just to sort of add. So the father of one of the most clever chemists of all time, this is Dmitry Mendeleev. So the periodic table that you've been seeing behind me, he basically created the periodic table. Absolute genius. He realized that all the elements that hadn't been found, they would be in certain spaces in that periodic table. And he predicted their qualities, their properties, and all sorts of different things. Really, really super clever chemist, okay? However, he didn't start it. So where did it all begin? So really the first person to identify the fact that I think in nature there are fundamental substances which are rather unique, okay, and they're pure. And this is Robert Boyle in the 1600s, basically saying, look, those primitive and simple bodies of which the mixed ones are said to be composed and which are ultimately resolved, okay. So he's the first person to really say, I think there are things called elements, okay. The next person is, of course, Antoine Lavoisier, a little bit later, and he basically said, fundamentally, there are substances which cannot be broken down. So that's the first time somebody said, actually, I think with things like pure iron, there's pure mercury, there's pure substances that can't be broken down. So these are people starting to now feel their way through into the natural world and the order of things. Then you've got John Dalton around about the same sort of time, and he basically sort of said, right, we need a concept in chemistry, and it's called atomic theory. Everything's made of atoms. Atoms are the fundamental building block of everything, and all atoms have a specific quality and a particular property. And so he basically introduced atomic theory. Okay, and then comes Johann Wolfgang Dobereiner, and he says, do you know what? Just like you, because you're going to see this. You're going to feel this. When you go into the swimming pool and you smell that chlorine, you are going to smell, you're going to whiff a little bit of this iodine, and everybody that smells iodine and everybody that smells chlorine goes, they sound very similar to me. They're very similar. And if you explore these elements in lots of different ways, Dobereiner is one of the first people to say, they somehow, can we group them together? Can we classify them? So he was one of the first people to say, I think there are groups of elements together. Chlorine, bromine, and iodine, very similar. And then, this is a bit more complicated, but this man here is called Julius Lothar Meyer, and he basically says, I've also noticed that there are certain elements in certain groups, the triads, they all react in the same way, or very similar way. And he's one of the first people to point that out, okay? So, we had a quick look at carbon. 3 basic types of carbon, okay? We've got graphite, we've got diamond, and we've got fullerenes, and that's what they kind of look like. And you all know what diamond looks like, and that's what they look like on the molecular structure. That's what their forms look like if you look at a microscopic form of them. We had a little look at sulfur. We've got a little bit of sulfur to play with. There's loads of different types of sulfur. The atom itself can bond in lots of different ways, can go into long chains or into little circular forms. So there's lots of different types. And I said, you see monoclinic. Can you see? That's what's formed in your little tray. It's some monoclinic needles of sulfur. It's one of the many different types of. Oh, I've got a hand. Got a hand. I can't see the purple. Sarah, hang on. Sarah, I'll be there in a second. Jake, go for it. Yes.
What are the bubbles coming off the ice?
Oh, the ice. That's a lovely question. That's just dissolved gases in the water, basically coming out because it's a little bit hot coming out. So it's just dissolved gases coming out because you've heated the solution. Nice question. Okay. Nice observation.
Thank you.
You're very welcome. Sarah. Now I can see well. Sarah, the purple has come. Purple rain. I was never going to be a singer. That was not my chance to hit stardom with Purple Rain or anything like that. Or to the point, a great film, Colour Purple. But here we have the MEL version of the Colour Purple. Okay, so I think, I've got tons and tons and tons of iodine. So I'll just finish off very quickly with that. Hang on. I think we've got to the end of... And then iodine, finally, before we go back to the reaction, just very quickly, very, very briefly, iodine, it's really, really, really kind of rare on the Earth. There's not a lot of iodine on the planet. It's largely found in seaweed, so eat some seaweed. That's why the Japanese are so healthy, because they eat lots of seaweed, because it's full of iodine. Because if you don't have iodine, particularly if you're young, it can stunt your growth, it can stop your development, it can stop your brain forming, and also it can cause a horrible disease called goiter, which is really shocking. So you must have iodine in your diet, okay? It's why they put iodine in salt, to have iodized salt. And of course it was discovered in an attempt by Napoleon to find another way of making gunpowder. And they made it from seaweed. Okay, cool. Oh, Jake, another question. Go for it. Kirsten and Ed, what's happening? Hang on, Kirsten, I'll be right with you.
Dan, I've got crystals forming around the cup now. Is that the iodine gas turning into a solid?
Yeah, no, it's not turning. It's the gas which is subliming into a solid. So it's going from a gas straight to... Because normally, remember, you've got to go from a solid to a liquid to a gas. And iodine is one of the few substances like dry ice. You know, we see dry ice. It goes from a solid straight to a gas. So this is going straight from a solid to a gas and then back to a solid again, okay, without going through a liquid.
Oh, okay. Thank you.
You're very welcome. Kirsten and Ed, can I unmute you? Kirsten, Ed, speak to me. What's happened?
We've got sparkles.
You have sparkles. You should have a lot of sparkles, right? Now, so take care. Don't touch the. You should have your gloves on, but you shouldn't touch those iodine crystals. Not going to be the end of the world. I'm going to show you what happens when that happens. Okay, so don't panic. Don't panic. Right. So look at my. If you've got that, we've got about 10 minutes now, so can you please blow out your candles? If you can see the iodine crystals, I'm going to blow out my candle now. Look. So blow out that candle and just wait for a couple of minutes. Just wait for a couple of minutes. Just wait for a couple of minutes. I'm going to just tip out a bit of water out of mine. In fact, what I'm going to do, because I want to show you a little bit of the chemistry here, which is what it's all about, of course. Just going to pull that out and just pour a little bit of that liquid away, just a little bit away. Now you should see, but do not pour that liquid all away. You should see some beautiful crystals of iodine on the side of the gas. Okay, so once you've done that, if you just pour that liquid into the, after about 3 minutes. You wait about sort of 3 minutes or so, because what we want to do is wait for the glass to cool. Because if you pour the icy water into the glass, of course, it will shatter, okay? But I know that some of you have, don't worry about this, some of you have, a little bit like me, have taken the plastic beaker out of it. You should have seen those little wisps of iodine vapor appearing, okay? That is the sister or the daughter or the son or the brother, however you want to see it, of chlorine, okay? That's of chlorine. And what you can do is what's called the waft test. I'm just going to take that out very, very briefly here like this. And if just from the surface, do not stick your nose in that glass at all. If you do it very slight, you can probably smell a very similar chemical smell to chlorine, okay, and that is iodine. They're all part of the triad family that Dobereiner sort of said, just that little waft test. Do not stick your nose in it, do not at all. And now we actually need to quench that reaction, okay? So what I'm going to do is pour that whole of that solution into the glass now to stop that reaction and make the purple disappear. But carefully, and just give that a little stir around, and you'll see that all of that purple colour has disappeared now. So it's reacted with the sodium thiosulfate solution, and the iodine has gone from a elemental iodine into a compound. Okay, so iodine ions now in solution. But beautifully, look at those beautiful iodine crystals, and if I shine a little bit of a light on it, you should see it nicely sparkle. I don't know, it's not capturing here. It's a little bit of sparkly. So there's a little pure elemental iodine. You have now seen for the first time elemental iodine going from a liquid, from a solid to a gas to a solid. And now here's the thing. This is why you don't touch the iodine. Look. Has anybody ever had a cut and had a spray from the doctor and the spray's been orange? Anybody? Has anybody had a cut and had a spray and it's gone orange? Anybody? Yes. Well, this is it. Look. If I don't do this. If you've got gloves on, you could do this. But if you just touch that, you can see that strange orange colour appear. That's because that orange spray contains iodine. And generally speaking, it's something called Lugol solution. And I can actually show you a bit of Lugol solution. Hang on. So you see, look, that's the colour that iodine stains my hand, okay? So it's not the end of the world. So if you've got your gloves on, that's why you're wearing gloves. But here's the Lugol solution, of course. That is iodine dissolved in a little bit of alcohol and water. And I'm just going to take a little bit off and just show you the colour. See, on this one, look, on my hand here, can you see it's the same colour? It's the same colour. So that's Lugol solution, okay? Okay, which is why you wear gloves when you're doing these reactions. Okay, so once you've seen that, and you've seen the pure elemental crystalline iodine, we now need to make sure that we've disposed of this iodine safely, okay? So what you need to do is pop your beaker into that beaker again, okay? So if you just do that, look, and it will mysteriously disappear. So just turn it around and rinse it around and rinse it around and rinse it around. Okay, and all of that iodine should have then disappeared. However, my dad cut his finger and the hospital put his finger in it, which I think was an iodine solution. Was this to clean it? Julie, fantastic observation, yeah. Iodine is a fantastic antibacterial, okay? It basically kills, like, you know, when you put chlorine in swimming pools, it basically kills all of the bacteria. It breaks up the cell membrane very, very efficiently of all bacteria and all viruses. I mean, literally, nothing is getting past that. And iodine does the same thing. In the same family, remember, they have the same properties or similar properties. Iodine is a lot safer. However, for those, if you're in Europe, possibly in the States, you might have come across a compound called TCP. Anybody heard of TCP? Yeah? So TCP is a compound called trichlorophenol. Okay, so trichlorophenol, and basically that chlorine element is one of the bits that really, as phenol also does the job, but breaks the membrane of the bacteria and the viruses. And iodine solution does the same thing. But interestingly, another observation here, did anybody see that the beaker itself has kind of stayed yellow? Anybody seen the beaker's kind of stayed yellow? No? If you produce a lot of iodine, okay, yeah, that's brilliant. If you didn't, don't panic. If you don't panic. But some of you may have produced a lot of iodine, okay, depending on the amount of the reagents you added. But the reason it stayed yellow is the fact that the iodine has snuck through the molecules of the plastic. It's snuck through the molecules of plastic. It's actually diffused through the plastic. Iodine's a very creepy little substance, and it's actually diffused through the plastic. And actually, one of the MEL kits that you'll get in time, it shows you how iodine diffuses through different substances. So it's a really rather wonderful element indeed. Okay, cool. Right, back to fake exam. Was that okay? Was that a bit of fun? Cool. It's just such lovely. And thank you. You're being so patient, Julie and family and so on and so forth. Being very patient, just sort of watching. But I really hope that when you get your kits and you do the kits, you're going to really enjoy this fundamental bit of chemistry. And it is just one. I mean, this is the most amazing table in the world. And remember, if it's not on here, it doesn't exist. This basically makes you, the plants, the universe, the carpet, the cat, the sky, the sun, the stars, everything. So this is just wonderful stuff. Cool. Are there any questions? Yay, you did. Arthur, thank you very much, Arthur. Thank you. Have you got any questions? You can unmute if you'd like. Where are you doing the lesson from? Adam, I'm doing the lesson from Birmingham. So my lab in Birmingham. So the company is in the States and it's in Europe and in the UK. So hopefully that was okay. I hope you enjoyed that bit of stuff. But please do, you can ask. I'm here. Cool, I'm in Anglesey. Hey, Anglesey. Lovely Anglesey. Very beautiful little part of the world, that is. Yeah. Any questions? Any questions at all? It's a live webinar, so you've got plenty of opportunity to ask questions. All you've got to do is put your hand up and I can unmute you. Julie, you're very welcome. Thank you so much, Julie. It's an absolute pleasure. Delight. Any other questions? Got Julie go. Yes, Julie. Hello.
How many elements are in the periodic table?
At the moment, it's up to 118. So if you see right down here, look, can you see the bottom one here? This one here, Og. It's got the funny little Og, Oganession. Yes. There's only about 10 atoms of that element, because you actually they have to create these elements from most of these elements along here. Look, from niobium all the way through moscovium to oganesson. They have to make those by bombarding big atoms with other atoms, okay, in sort of nuclear reactors, and trying to make bigger elements. So at the moment, and this is where you see it's quite nice and synchronous, this periodic table. It's got like a little box structure, and this element here, look, you think, well, is there another element going out there? Is there another element that we're going to add on here or add on the bottom, or who knows? Really, who knows? This is one of the weird things about elemental chemistry. But lovely question.
Sorry, can I just ask what your favourite element is?
I have to be perfectly frank. By miles, my favourite element has to be carbon. You know, it has a whole branch of science all on its own. Of all the elements in the periodic table, in every chemistry department in every university around the world, there is always an organic chemistry department, and the organic chemists, all they do is they muck about with carbon. It's just so beautiful. I call it the Care Bear of elements. Okay, so in terms of reactions, what I mean by that. So these ones here, okay, on this side, so the alkali metals, the alkali earth metals, or whatever. They're desperate to give away an electron and form a nice stable reaction. So they just give them away, okay? And this group 1 is very keen to give them away. Give them away. Group 2, give them away, but less easy to give them away. Then group 3, I really want magic 8 in my number. Yeah, okay, we'll give you away. But then when you get to carbon, this group here, carbon, silicon, whatever, they've got 4 electrons on their outer orbital, 4 electrons. And to get 8, it's as easy to get 8 as it is to give 8. So it's a kind of share-bear kind of situation. And it's so easy going, so happy going, this element. It just react with practically anything. And it loves itself. So you find massive long chains of carbon atoms, or big circles, or the fullerenes, 60 atoms of carbon in a big sort of ball. It's amazing. But that's not to say that all the rest of the elements have lots of little stories to tell on their own, and they are remarkable. Each element has a whole little history, which is just beautiful. So, yes, thank you.
Thank you.
You're very welcome. Jake.
What happens to the crystals crystals on the outside of the cup when you put them in the solution?
Right, so the sodium thiosulfate, so the iodine is elemental iodine at this stage. So it is an atom. Okay, it's an atom. It's got no charge either way. And it's going, hello, okay, I'm in the room. I'm finally free. But actually, the iodine is like a halogen. They don't hang around for long. They're just looking for stuff to react with, okay? So it might look like a little crystal going, ah. Nah, it was busy trying to react to something. So when you put it in the sodium thiosulfate solution, the iodine is reacting with that compound and it's forming iodine ions in solution. So you see, when you saw the potassium iodide, did that look purple?
Yeah, no.
No. Did it look metallic? No. So that is iodine ions wrapped in with the potassium, okay, in a different format. And so similarly, it's now gone into solution. So actually, you could crystallize that solution, so evaporate that solution out, and you'll get, lo and behold, a white crystalline solid. So it has reacted and got into a solution. Nice question. Got another question. Kirsten and Ed, and I see Julie as well. So yes, Kirsten and Ed first.
Would it ever be possible, even in the slightest, for any form of life to be based off something other than carbon?
Definitely. Adam, sorry, just before I answer that question, Adam's saying goodbye. So thank you, Adam. Thank you so much, Adam. An absolute pleasure to have you on board, and thank you for subscribing to MEL. I hope to see you again soon. Kirsten Ed, beautiful question. Can you see the group that carbon's in? The one beneath it is silicon.
Yeah.
So silicon, again, also forms 4 bonds on its outer electron. So that's in group here, 4, okay? And scientists can also refer it to a different thing, but make it simple, it's in group 4. So it forms 4 electrons on its outer side. It's a bigger element, a bigger atom. But could there be silicon-based life forms? Very definitely, very definitely. Have we seen any of them in space? No, because we haven't seen any other life forms in space. But just as a kind of little insight, you know the White Cliffs of Dover, because I'm assuming you're in the UK. So you've got the White Cliffs of Dover. So it's all basically chalk. It's made of chalk, isn't it? That's because the chalk itself is made of loads and loads, billions and billions and billions and billions and billions of little tiny creatures called foraminiferae or coccoliths, little tiny creatures. You can look this up online. And their bodies, like our bodies, are made of calcium. Okay, they're made of calcium. However, if you look at those White Cliffs of Dover, you'll see little blobs of black rock in there. And it's called chert. That's called chert, okay? And that's made from the bodies of little creatures called radiolarans. And their bodies are made of silica. Their bodies are made of silica. So their bones are made of silicon. So whilst the outside of the radiolara, of course, is a carbon-based life, its little skeleton is silica. So possibly in the realms of space, it may well be possible that there are silicon-based life forms. Yes, lovely. Good question. Lovely question. Julie. Go for it.
What elements are human made of?
Oh, lovely question. So the fundamental element that you're made of, carbon, hydrogen, nitrogen, oxygen, and sulfur, are the main elements in you, okay? Are the main elements in you. And so... you know your DNA, deoxyribonucleic acid, is basically a phosphor group with a sugar group, so loads of carbon rings around it, and the little hands are little phosphors, elemental phosphorus rather, and then you've got sulfur in there too. So those are the core ones. You're basically, most of you at any one point in time is water, of course, and of course water is H2O, so a big chunk of you is basically water. Your bones are basically largely calcium. Your teeth are made of an element compound called calcium fluorapatite. So when you a toothpaste, have you noticed that in your toothpaste they add fluorine? So this is elemental fluorine. Not very much of it, but your teeth have fluorine in that compound, calcium fluorapatite, okay? So the majority of it. But you have all sorts of really curious things in your body. If you look at the periodic table behind me, can you see an element called molybdenum? Can you find an M, molybdenum? Somewhere roughly here?
Yeah, see, I found it.
So what is it? M what, Holly? Tell him what it is.
M-O.
Lovely. Lovely. You've even got that in you. And actually, if you took that element out of you, you would be very, very, very unwell. But the amount of that that's in you is less than a match head. Okay? You would be very, very, very unwell. In fact, can you see another element in there called selenium? Can you see selenium anywhere?
Is it C or S?
S.
Oh.
See an element called selenium?
SC?
Ah, excellent. Well spotted. Well spotted. Very interestingly, they weren't really super aware of the importance of selenium in the body. It's absolutely essential, by the way, until a study in about I think it was the 1960s, discovered in China. There was a city that straddled a river. The river flowed down a fault line. And so they studied, there was an interesting epidemiological sort of study that was carried out, and they found that people on one half of the river had a higher prevalence of heart attacks than the other side of the river. And they then did lots and lots of study to find out why this was happening. And they found out that rock on one side of the river actually was more deficient in selenium than on the other side of the river. So it's a really interesting element, and one of the reasons, not all the elements have any role in your body. So, for example, my wedding ring, for example, is made of palladium. So you can see if you can find palladium. And palladium plays no part in the human body at all, anywhere. However, copper has lots and lots and lots of things to do in the body. If you took all the copper out of your body, if I had a magic wand and I took all the copper out of your body, you'd die almost immediately. So all these elements are really, really fascinating. There's not much aluminium in your body, but yeah. Cool, nice question.
Lovely. Thank you.
You're very welcome. Any other questions? As you might guess, I quite like questions. I don't... another question from Kirsten and Ed. Yes?
So, what is the most common element, minus carbon?
Oh, right. Well, in the universe, if you take the universe as a whole, the most common element that counts for over 90% of it is hydrogen. So this one here, this is the mother of all elements. So all your stars and stuff like that are burning hydrogen, okay? The next one is helium. And those are the two that make up the majority of the whole of the universe. And then your homework, of course, is to go and find out which element is number 3. And that might come as a surprise, but it is here.
I'm going to make a guess and say it's oxygen.
Pretty good guess. And then you've got to roll on to element 4 and so forth. It's a fascinating study. Of course, all of these elements, apart from hydrogen, sorry, keep pointing the wrong thing, apart from hydrogen, all of these elements are made in stars. Is it he or hi? Sorry, Sarah. Little joke, nice. Is the fourth one nitrogen? Ah, that, Julie, is for you to do some a little bit of homework. However, if you want to do this, you want to do a bit of research, which is absolutely fascinating. You need to look up stellar burning, or stellar burning, and look at elemental formation. Okay. So if you go to,
I froze.
did I freeze? I haven't frozen. Have I frozen? I don't think so. Hopefully I haven't. At what time? I hope I haven't frozen.
Yeah.
So the
I froze.
You froze. So in stars, basically, what's called stellar burning. So basically what's happening in stars is that hydrogen and hydrogen are combining together at massive speeds under huge pressures at high temperatures. They're colliding together to form helium. So they're under here. So hydrogen form helium. And then helium combines with hydrogen and so on and so forth to form all of the other different elements, etc., right up until you get to iron. All of the elements after iron you can only form when you have what's called a supernova, so when the star basically explodes. And when a star explodes, well after its lifetime, there's enough energy available for all of the other little nuclei to fuse together to form all of the heavier elements. So things like, for example, gold only form when you have a stellar explosion, okay? But everything else in the moment. So if you look at our star is basically made up of all these top row elements up until iron. Okay. Any other questions? Hope that's okay. No questions? Cool. In which case, it is Friday soon. So it leaves me to say thank you so much once again for subscribing to MEL. I hope that's been interesting. I hope that's been lovely. And I really wish you have a fantastic weekend. And I really look forward to seeing you all again, hopefully next week at some point. So, Jake, take care. Stay well, and I will see you soon. If you've got any other questions, please just send them to support@mel.com. Send them to me, and they'll come back to me, and then I can answer your questions, and I'm very happy to do that. So thanks once again, and I will see you. Goodbye.